Welcome to Jeremy's IT Lab. This is a free complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. Today we will finish our studies of OSPF for this course. Already we've covered OSPF in much greater depth than RIP and EIGRP. If you continue your studies to the CCNP and CCIE level, you'll see that there is much more depth to OSPF. However, for the purpose of this CCNA course, we'll finish up our studies with this video. Once more, here is exam topic 3.4, which covers OSPF. After today's video, you'll be more than ready to take on OSPF questions on the CCNA exam. So let's get started. First, let's look at what we'll cover in this video. First up, OSPF network types. These refer to the different kinds of connections between OSPF routers and how those connections influence OSPF's behavior. Next up, we will cover OSPF neighbor and adjacency requirements. In day 2, we covered the process routers use to become OSPF neighbors. However, we didn't actually look at the requirements for a successful neighbor adjacency. Then we'll take a look at a few of the LSA, link state advertisement types. There are many, but you only need to be aware of a few for the CCNA. Make sure to stick around until the end of the quiz for a bonus question from Boson ExSim for CCNA, the best practice exams for the CCNA. Before we get into those topics, I want to take a minute to explain loopback interfaces a little bit. In previous videos, I've mentioned them, and you've already practiced configuring them in the past few lab videos, but let me explain them a little more. A loopback interface is a virtual interface in the router. You already know that. It is always up, unless you manually shut it down. So this means that the status of a loopback interface isn't dependent on a physical interface. Physical interfaces can have hardware problems and fail. However, that can't happen to a loopback interface, unless the router itself fails. So it provides a consistent IP address that can be used to reach and identify the router. Sometimes you need to send traffic directly to a router. Let's say R1 has no loopback interface at the moment, and R4 receives a packet destined for R1 at 10.0.13.1, the IP address of its G10 interface. It might forward it to R1 like this. What if R1's G10 interface goes down for some reason? If R4 receives a packet destined for R1 at 10.0.13.1, it will not be able to send the packet to R1. How about if R1 has a loopback interface, 1.1.1.1, and that is used to identify R1 instead of 10.0.13.1? Even if a physical interface fails, when R4 receives a packet destined for R1's loopback interface, it will still be able to send the packet to R1. So that's why it's a good idea to configure a loopback interface on a router. It provides an interface with an IP address that is always up, and can consistently be used to identify and reach the router. Now let's move on to look at the different OSPF network types. The OSPF network type refers to the type of connection between OSPF neighbors, and the type influences how OSPF behaves in some ways. The most common type of connection in modern networks is Ethernet, of course. There are 3 main OSPF network types. The first is the broadcast network type, which is enabled by default on Ethernet and FDDI interfaces. FDDI is an old technology, and you don't need to spend time learning about it. However, I will include it in the flashcards for OSPF network types. You might want to remember this one fact about it for the exam, that the OSPF broadcast network type is used by default. The next is the point-to-point network type, which is enabled by default on PPP and HDLC interfaces. You don't need to learn PPP and HDLC in depth for the current CCNA exam, but I will mention them briefly later in this video. The last main network type is non-broadcast. It is enabled by default on frame relay and X25 interfaces. Again, you don't need to learn about these interface types for the exam, but I will include them in the flashcards for this video regarding OSPF network types. Take a look at the OSPF exam topics again. 3.4b mentions the point-to-point network type, and 3.4c mentions the broadcast network type. So, those are the network types we will focus on now. First up, the broadcast network type. As I just mentioned, this network type is enabled on Ethernet and FDDI interfaces by default. For this course, our main focus is Ethernet, and in the previous videos, all of the OSPF connections we've looked at have used the broadcast network type, because they are all Ethernet connections. In the network diagram above, these are all Ethernet connections. Remember, G means gigabit Ethernet, and therefore these connections between the routers are all using the broadcast network type. Now let's cover a few characteristics of the broadcast network type. First up, routers dynamically discover neighbors by sending and listening for OSPF hello messages using the multicast address 224.0.0.5. You already know this from the previous video, when I showed you how OSPF routers become neighbors. However, not all network types dynamically discover neighbors like this. We won't cover this network type, but with the non-broadcast network type, you must manually configure neighbors. Okay, next point. A DR, designated router, and BDR, backup designated router, must be elected on each subnet. However, in cases like the G10 interface of R1, R3, R4, and R5, where there are no OSPF neighbors, there is just a DR, no BDR. Routers which aren't the DR or BDR for the subnet become a DR other. I've heard a few ways to pronounce that, but I say DR other. So let's look at the network above. Each subnet needs a DR. These subnets are easy. There are no OSPF neighbors, so each router becomes the DR for the subnet. How about the 192.168.1.0/30 subnet between R1 and R2? In the next slide, I'll show you how the DR is elected, but let's say R2 is the DR. So, R1 becomes the BDR for the segment. How about the 192.168.2.0/29 subnet that R2, R3, R4, and R5 connect to? For example, R5 might be the DR, R4 the BDR, and then R2 and R3 become DR others. You're probably wondering how these elections work, and what the purpose of the DR and BDR is. Well, let's get into it. So here's how the DR and BDR are elected. There is an order of priority. First up, the router with the highest OSPF interface priority in the subnet becomes the DR for the segment. However, all interfaces have the same priority by default, so then the routers compare their OSPF router IDs. The router with the highest OSPF router ID wins. First place in the election becomes the DR for the subnet, and second place becomes the BDR. The default OSPF interface priority is 1 on all interfaces. So, as I said, by default the router with the highest router ID will become the DR for the segment. Here's some partial output from show IP OSPF interface G00 on R5. Notice the router ID. I configured a loopback interface on each router, and the IP address of the loopback interface became the router ID. State DR, and the priority is the default of 1. R5 has the highest router ID of the routers connected to the 192.168.2.0/29 subnet, so it became the DR. Down here the DR, R5 itself, and BDR, R4 for the segment are listed, including their router IDs and the interface IP address in the subnet. And here's the same output for R2. The main difference I want to point out is the state of DR other. Now what if I want to make R2 the DR for the segment instead of R5? Let's see how to change the OSPF interface priority. The command to change the OSPF priority of an interface is IP OSPF priority, followed by the priority, with a range of 0 to 255. I changed it to the maximum, 255 on R2. As a side note, if you set the OSPF interface priority to 0, the router cannot be the DR or BDR for the subnet, no matter what. So let's check if R2 has become the DR for the segment. That's strange. R2's state is still DR other, even though it has the highest priority. Why is that? It's because the DR-BDR election is non-preemptive. You'll learn more about preemption in day 29 when we learn about first-hop redundancy protocols. But what non-preemptive means is that once the DR and BDR are selected, they will keep their role until OSPF is reset, the interface fails, is shut down, etc. So, although this is a bad idea to do in a live network, I'll go reset the OSPF process on R5, and let's see what happens. So, I reset the OSPF process on R5, and you can see that all of its neighbors went down. Then R2 and R4 returned to the full state, but not R3. There's an important reason for that, you'll learn soon. Then I used the show IP OSPF neighbor command to view the neighbor state of R5's neighbors. Look here, there are two important points about OSPF we can learn by analyzing this section. First, R4 became the DR, not R2. R2 became the BDR. What can we learn from that? We can learn that when the DR goes down, the BDR becomes the new DR. Then an election is held for the next BDR. R4, which was the BDR, instantly stepped up to be the new DR, and then an election was held between the other routers for the next BDR. R2 has the highest priority, 255, so it became the BDR. Okay, next point. R3 is a DR other, and is stable in the two-way state. R5 became a DR other also, by the way. What can we learn from this? We can learn that DR others will only move to the full state with the DR and BDR of the subnet. The neighbor state with other DR others will be two-way. This gives us a hint to the purpose of the DR and BDR, which I'll cover in the next slide. But remember these 2 points, that the BDR becomes the DR if the current DR is removed, even if it doesn't have the highest priority. Also that DR others don't form full adjacencies with other DR others. They remain in the two-way state. To repeat, in the broadcast network type, routers will only form a full OSPF adjacency with the DR and BDR of the segment. Therefore, routers only exchange LSAs with the DR and BDR. DR others will not exchange LSAs with each other. Remember that in the two-way state, routers haven't shared LSAs with each other yet. All routers will still have the same LSDB, but this reduces the amount of LSAs flooding the network. Let's see an example. If 6 routers are connected to the same segment, and they all share LSAs with each other, it will end up like this. A whole lot of LSAs flooding and congesting the network. How about if we use a DR and BDR? If routers only exchange LSAs with the DR and BDR, as you can see, the number of LSAs flooding around the network is reduced. To be honest, on modern routers, it's probably not a big deal in most cases, but it still does help reduce unnecessary network traffic. By the way, when routers need to send messages to the DR and BDR, they use multicast address 224.0.0.6. This is different than the OSPF all routers multicast address of 224.0.0.5. Here's a quick review of the OSPF neighbor process. Remember that I said these first steps involve becoming neighbors? So when routers reach this point in the process, they are OSPF neighbors. Connections between 2 DR others stop at this point. Routers will only continue on to exchange LSAs and form a full OSPF adjacency with the DR and BDR. So to summarize, this means that the DR and BDR form a full adjacency with all routers in the subnet, including the DR others. And DR others will form a full adjacency only with the DR and BDR. I showed you this command, show IP OSPF interface brief, before. Here I did it on R3, which is a DR other. Notice the neighbor count on its G00 interface. F indicates the number of full adjacencies, and C indicates the total count of neighbors. So R3 has 2 full adjacencies, with R2 and R4, but it has 3 total neighbors, R2, R4, and R5. For more detail, here is show IP OSPF interface G00 on R3. It gives the same information here. Neighbor count is 3. That's R3's total number of OSPF neighbors. Adjacent neighbor count is 2. Those are the neighbors R3 has formed a full adjacency with. And below it, its two adjacent neighbors are listed: R2, the BDR, and R4, the DR. Okay, that's enough for the broadcast network type for now. Let's move on. Now let's take a look at the point-to-point network type. Notice that I changed the connection between R1 and R2 to a serial connection. I will give a very brief overview of serial connections in the next slide, but first let me introduce the basics of the point-to-point connection type. This network type is enabled on serial interfaces using the PPP or HDLC encapsulations by default. PPP and HDLC are both layer 2 encapsulations, similar to Ethernet, except they are used on serial connections. Same as the broadcast network type, routers dynamically discover neighbors by sending and listening for OSPF hello messages using multicast address 224.0.0.5. However, here's the difference. A DR and BDR are not elected. Why is that? As the network type name implies, these encapsulations are used for point-to-point connections between two routers. Therefore, there is no point in electing a DR and BDR. The two routers will form a full adjacency with each other, without the need to elect a DR and BDR. Okay, let me give a very brief overview of serial connections. I say very brief because serial connections are an old technology which isn't very common anymore. They still exist, but Ethernet is much more dominant. In fact, serial connections have been removed from the exam topics, except for the OSPF point-to-point network type. So, although you won't be tested directly on knowledge of serial interfaces, you should have a basic understanding of them. This photo shows some serial interfaces and cables. Notice that both the ports and the cables are different than Ethernet cables. To explain serial connections, I'll show you how I configure R1's S20 interface. You don't need a deep understanding of this material, but at least know the basics I introduce here. First up, one side of a serial connection functions as DCE, which stands for Data Communications Equipment. The other side functions as DTE, which stands for Data Terminal Equipment. Why is this significant? Well, on serial connections, the DCE side needs to specify the clock rate, which is the speed of the connection. So, in this case, R1 has the DCE side of the cable, and therefore needs to tell R2 what speed the connection will operate at. The command is clock rate, and then you can see some standard values that can be used. All of these are in bits per second, by the way. I configured a clock rate of 64,000 bits per second, aka 64 kilobits per second, added an IP address, and used no shutdown. Here's an important point. Ethernet interfaces use the speed command to configure the interface's operating speed. Serial interfaces use the clock rate command. Let's continue. I checked the interface with show interface S20. Notice that the encapsulation is HDLC. On Cisco routers, the default encapsulation on a serial interface is HDLC. Actually, it's Cisco's own version called CHDLC, Cisco HDLC, but it displays as just HDLC in the CLI. Once again, this is a layer 2 encapsulation, like Ethernet, except it's used on serial connections. Here's the structure of an HDLC frame, taken from Wikipedia. You don't need to learn this, but pause the video if you want to take a look. One thing to note is that there is no MAC address field, so MAC addresses actually aren't used. I mentioned the PPP encapsulation too. Let's see how to configure the router to use that encapsulation instead. Simply use the encapsulation PPP command on the interface. Note that if you change the encapsulation, it must match on both ends or the interface will go down. If they use two different encapsulations, it's like they are speaking two different languages. They won't be able to communicate. I did show interface S20 again, and you can see the encapsulation has changed to PPP. I did the same on R2, by the way, so the interface is up. Here's the configuration I did on R1. The serial restart delay 0 command was there by default, so I only configured the clock rate, encapsulation, and IP address. And here it is on R2, with no clock rate command because it is the DTE end. Now you're probably wondering, how can I tell which side is DCE and which is DTE? Well, to show you, I had to recreate this connection in Packet Tracer. GNS3, which I use to make these lectures, doesn't handle physical layer 1 things like this well, so both sides display as DCE. Anyway, the command to view it is show controllers, followed by the interface ID. As you can see, R1 is the DCE side, and it has the clock rate of 64,000 bits I configured. I used the same command on R2, and you can see it is the DTE side, and it has detected the TX, transmit, and RX, receive, clocks from R1. So that's a very basic overview of serial connections. Here's a summary of what you should know. The default encapsulation on a serial interface is HDLC. You can configure them to use PPP encapsulation instead with this command, encapsulation PPP. If you change the encapsulation on one side, remember to change it on the other too. One side of the connection is DCE, and the other is DTE. You can identify which side is DCE and which is DTE with this command, show controllers, followed by the interface ID. Finally, remember to configure the clock rate, the speed of the connection, on the DCE side with this command, clock rate, followed by the clock rate in bits per second. Let's return to the OSPF point-to-point network type. Here's the output of show IP OSPF neighbor on R2. Notice that R2 has a full adjacency with R1, but instead of DR, BDR, or DR other, a dash is displayed. This is because the point-to-point network type doesn't use DRs or BDRs, as I mentioned before. Final point on this topic. You can manually configure the network type an interface uses. The command is IP OSPF Network, followed by the network type. You might notice one more type that I haven't mentioned. That is the point-to-multipoint network type. It's more of a subtype. You don't need to learn about it for the CCNA, but feel free to do a Google search if you're curious. So why would you change the OSPF network type? For example, if two routers are directly connected with an Ethernet link, like in the diagram below, there is no need for a DR and BDR. You can configure the point-to-point network type in this case, although you don't have to. Note that not all network types work on all link types. For example, a serial link cannot use the broadcast network type. This is because serial links don't support layer 2 broadcast frames, which is necessary for the broadcast network type. Okay, here's a chart for a quick review. One thing I didn't bring up yet in this video is that point-to-point networks use the same default timers as broadcast networks. The default hello timer is 10 seconds, and the default dead timer is 40 seconds. You don't have to learn this network type, but just for your information, the non-broadcast network type uses a default hello timer of 30 seconds, and dead timer of 120 seconds. Okay, let's move on. Now let's move on to look at some requirements of OSPF neighbor relationships. Usually, routers will become OSPF neighbors without issue, but I will introduce a few of the problems that can occur. I already mentioned some of these in previous videos, but let's review. First requirement, the area number must match for two routers to become OSPF neighbors. We'll use this small topology of two routers to demonstrate. Here's R1's OSPF config. OSPF is enabled on G00 in area 0. However, R2's G00 is in area 1. When I enter show IP OSPF neighbor on both devices, they have no OSPF neighbors. Let's fix the issue. I changed the network command on R2 to use area 0. As you can see, they successfully became OSPF neighbors. So that's the first rule. For two routers to become OSPF neighbors, they must be in the same area. But we already covered that before. Next rule. The interfaces must be in the same subnet to become OSPF neighbors. We covered this one before too, but let me demonstrate it. Notice that R1 and R2's G00 interfaces are now in different subnets. I activated OSPF on both of the interfaces, but when I check for OSPF neighbors, they don't come up. I once again configured R2's interface in the same subnet as R1, and also made sure to edit the network command so that OSPF is once again activated on G00. Now R1 and R2 are OSPF neighbors again. Next up, here's one we haven't covered yet. the OSPF process must not be shut down. You can actually shut down the OSPF process on the router like an interface. This disables OSPF operation without removing the OSPF configurations. Let's check it out. Here's how to do it. From OSPF configuration mode on R2, I use the shutdown command. Then a message is displayed indicating that its neighbor R1 has gone from full to down, and no neighbors are displayed in Show IP OSPF Neighbor. Then I enable OSPF again with no shutdown. A message indicates the neighbor is back up, and you can see it in Show IP OSPF Neighbor. That one won't be a problem unless you manually shut down the OSPF process, so usually it's not a problem. Next requirement, the OSPF router IDs must be unique. Let's see how that works. I haven't configured the router IDs of R1 and R2, and I also haven't configured any loopback interfaces. So each router has selected its G00 IP address as its router ID, 192.168.1.1 for R1 and 192.168.1.2 for R2. So I configured 192.168.1.1 as R2's router ID, the same as R1's. As I have shown you before, you need to reload the router or use clear IP OSPF process for the new router ID to take effect. So I used clear IP OSPF process. Immediately the neighbor goes down because I cleared the OSPF process. But then instead of the neighbor coming back up, this message is displayed. OSPF detected duplicate router ID 192.168.1.1 from 192.168.1.1 on interface gigabit Ethernet 00, and then the neighbor stays down. So let's fix this. I removed the manually configured router ID with no router ID. Note that you don't actually have to specify the router ID when removing the command. No router ID has the same effect as no router ID 192.168.1.1. Both remove the command. This time, without having to reset the OSPF process, R2's router ID returns to 192.168.1.2 and the neighbor comes up again. Why didn't I have to use clear IP OSPF process? I actually didn't expect this, but I realized that it's because R2 had no other OSPF neighbors at the time, so the router was free to change R2's router ID without worrying about it affecting other neighbors. So watch out for duplicate router IDs. Next requirement. The hello and dead timers must match. In both of the network types we looked at today, broadcast and point-to-point, the defaults are 10 seconds and 40 seconds, but you can manually change these settings. The hello and dead timers are configured directly on the interface. Here's how to configure the hello timer. IP OSPF hello interval, followed by the interval in seconds. I set it to 5. Then the dead timer. IP OSPF dead interval, and I set it to 20. As you can see, the neighbor then goes down. Note that I changed both values, the hello timer and the dead timer, but even if you only change one, the neighbor will still go down. So let's fix this. I used no IP OSPF hello interval and no IP OSPF dead interval to return the timers to their default values. Notice the method I used to return them to their defaults. It's the same as for the router ID. I didn't have to actually specify no IP OSPF hello interval 5 or dead interval 20 to remove the commands. Anyway, now that the hello and dead timers match again, the neighbor is back up. So remember to check the hello and dead intervals if you're having trouble with OSPF adjacencies. Next up, authentication settings must match. What does that mean? Well, you can configure an OSPF password, and then the router will only become neighbors with routers that have a matching OSPF password. Let's take a look. The OSPF password is configured directly on the interface too. I used IP OSPF authentication key, followed by a password of Jeremy. Note that this doesn't actually enable OSPF authentication on the interface. The password is configured, but we need to enable OSPF authentication. So I used IP OSPF authentication to enable it on the interface. Then the neighbor goes down, because R1 isn't providing R2 a matching password. Actually, I haven't configured OSPF authentication on R1 yet, so it's not providing R2 with any OSPF password. So to fix this, we could either configure the same authentication settings on R1, or remove the authentication from R2. I removed them from R2, and now the neighbor is back up again. Okay, there are two more things to mention. Number 7 is that the IP MTU settings on the interfaces must match. The IP MTU is the maximum size of an IP packet that will be sent out of the interface. The default is usually 1500 bytes, but it can be configured. Note that this requirement and the next one are special. Even if the settings don't match, the neighbors can become OSPF neighbors, but OSPF won't function properly. Let's see. You can configure the IP MTU of an interface with this command. IP MTU followed by the MTU in bytes. I changed it to 1400 on R2's G00, so it doesn't match with the default 1500 on R1's G00. I waited a minute and then checked the neighbor table. R1 and R2 actually remained neighbors. Then I reset the OSPF process on R2. I waited a minute, but no message came indicating that the neighbors had reached the full state. I checked the neighbor table again, and it was stuck in the XStart state. After waiting a few minutes, a few more messages were displayed, and these kept on repeating, by the way. So clearly OSPF isn't functioning properly. I used no IP MTU to return the MTU to the default value, and then finally R1 and R2 reached the full state. So if your OSPF neighbors are having trouble reaching the full state, make sure to check the MTU settings. Okay, last one. The OSPF network type must match. Let's see what happens if they don't. So to demonstrate this problem, I configured a loopback interface on R2 with an IP address and advertised it to R1. Then I changed the network type on R2's G00 to point-to-point. R1's G00 is still using the default broadcast network type. A message is displayed saying the neighbor went down, but then it went right back to the full state. R1 even displays as full in show IP OSPF neighbor. So what's the problem? Let's see on R1. Here's R1. R2 appears in the neighbor table in the full state, so you might think OSPF is working fine. But look at the routing table. R2's loopback address should be in R1's routing table, but it's not. This is what will happen when the OSPF network type doesn't match. It can be tricky to troubleshoot because the neighbor state is full, so it can seem like everything is working fine. Make sure to watch out for that when troubleshooting OSPF. Okay, I'll leave it there. There is, of course, more we can get into, but I've given you plenty for the CCNA. Make sure to remember these requirements. You don't have to memorize them as a list, but make sure that if you see these problems on a router, you are able to identify and fix them. The final topic for today's video is LSA types. These aren't specifically mentioned in the exam topics list, so I'm just going to spend a few minutes giving you a brief overview of some basic LSA types. To do so, I've taken this topology from earlier and modified it, adding an internet link on R4. R4 has a default route to the internet, and I use default information originate to make it advertise it to the other routers. So let's talk about LSAs. As you already know, the OSPF LSDB is made up of LSAs. All routers in the same OSPF area share the same LSDB. There are 11 types of LSA, but there are only 3 you should know for the CCNA. Those are Type 1, the router LSA, Type 2, the network LSA, and Type 5, the AS external LSA. Let's take a brief look at each type. First up is Type 1, the router LSA. Every router running OSPF generates this type of LSA. The router LSA identifies the router using its router ID. The router LSA also lists networks attached to the router's OSPF activated interfaces. Next up, the Type 2, aka network LSA. It is generated by the DR of each multi-access network. An example of a multi-access network is an Ethernet network, using the broadcast network type. This type of LSA lists the routers which are attached to the multi-access network. Last type for today, the Type 5, aka AS external LSA. This type of LSA is generated by ASBRs to describe routes to destinations outside of the autonomous system, the OSPF domain. Here's a look at the LSDB on R1 using the command show IP OSPF database. Note that it doesn't actually matter which router I use the command on. The output will be the same because all routers in the area have the same LSDB. Notice that each router has generated a Type 1 router LSA, identifying itself. This view doesn't show the contents of each LSA, but each of these router LSAs contains information about the networks each router is connected to. Notice that there is only one Type 2 network LSA, generated by R4 for the 192.168.2.0/29 subnet. Even though R1, R3, and R5 are DRs on their G10 interfaces, no other routers are connected to the interfaces, so no Type 2 LSA is generated. Finally, notice that a Type 5 AS external LSA is generated by R4. It is sharing its default route to the internet with the other routers. Okay, that's all about LSAs. Once again, they aren't explicitly stated in the exam topics list, but I just wanted to give you a basic introduction to some of the basic LSA types you will encounter. I told you we were going to cover OSPF in much more detail than RIP and EIGRP, and over these past 3 days, we definitely did that. OSPF is a major topic on the exam, so make sure you understand the material in these videos. Watch them multiple times if you have to, and feel free to ask questions in the comments section. Now let's review what we covered in today's video, and then move on to the quiz. First, we covered the OSPF network types, focusing on the two you need to know for the CCNA, broadcast and point-to-point. Because Ethernet connections are dominant in modern networks, most of the time you'll be using the broadcast network type. But also be familiar with the point-to-point type, and the basics of serial interfaces that I introduced in this video. Then I introduced some requirements for OSPF neighbors and adjacencies. You don't have to memorize the list of them, but make sure you can identify them all and fix any problems. Finally, I briefly introduced the three most basic OSPF LSA types. Type 1, the router LSA, Type 2, the network LSA, and Type 5, the AS external LSA. Make sure to watch until the end of the quiz for a bonus question from Boson ExSim for CCNA, my favorite set of practice exams for the CCNA. Now here's question 1 of the quiz. Which option states a characteristic of the OSPF point-to-point network type that is different than the OSPF broadcast network type? A. DR and BDR elections are held. B. DR and BDR elections are not held. C. Neighbors are dynamically discovered. Or D. Neighbors are not dynamically discovered. Pause the video to think about your answer. The answer is B. In the OSPF point-to-point network type, DR and BDR elections are not held. C, neighbors are dynamically discovered, is a correct statement about the point-to-point network type, but it is also true about the broadcast network type, so it is incorrect. Let's go to question 2. There is an OSPF broadcast network with 5 connected routers. R1 is the DR on its G00 interface. How many full OSPF adjacencies does R1 have on the interface? A. 1 with the BDR. B. 2 with the DR and BDR. C. 4 with all neighbors. D. 5 with all routers connected to the segment. Pause the video to think about your answer. The answer is C. The DR forms a full adjacency with all neighbors in the broadcast network segment, so C is correct. It doesn't form a neighbor relationship at all with itself, so B and D are incorrect. A is incorrect because it identifies only one of R1's fully adjacent neighbors, not all 4. Let's go to question 3. Which of the following are requirements for routers to become OSPF neighbors? Select 2. A. Hello and dead timers must match. B. OSPF process IDs must match. C. OSPF router IDs must match. D. Interfaces must be in the same area. E. Interfaces must be in different areas. Or F. Interfaces must be in different subnets. Pause the video to think about your answers. Select 2. The answers are A and D. For 2 routers to become OSPF neighbors, the hello and dead timers on their interfaces must match. They also must be in the same area. For reference, here are the requirements for OSPF neighbors as shown earlier in the video. Okay, let's go to question 4. Which of the following OSPF LSA types is generated only by the DR of a multi-access network, such as the broadcast network type? A. Type 1, B. Type 2, C. Type 3, or D. Type 5? Pause the video to think about your answer. The answer is B. Type 2. Type 2 is the network LSA and is generated by the DR of each multi-access network. It lists the routers which are attached to the multi-access network. A. Type 1 is the router LSA type. D. Type 5 is the AS external LSA type. C. Type 3 is one I didn't mention in this video. It's called the summary LSA type. Okay, let's move on to question 5. R1 is connected to an OSPF broadcast network on its G00 interface. R4 is the DR of the segment, and R3 is the BDR. All routers on the segment have the default OSPF priority. You issue the IP OSPF priority 100 command on R1's G00 to make it the DR. Which of the following statements are true about the network after you issue the command? Select 2. A. R1 is the DR. B. R1 is the BDR. C. R1 is still a DR other because its priority isn't high enough. D. If you issue the clear IP OSPF process command on R4, R1 will become the BDR. E. If you issue the clear IP OSPF process command on R4, R1 will become the DR. And F. The DR and BDR of the network are unchanged. Pause the video to think about your answers. Select 2. The answers are D and F. The default OSPF priority is 1 on all interfaces. So after entering the command, R1's G00 interface has the highest priority. Therefore, C is incorrect. It's still a DR other, but priority isn't the problem. The DR and BDR will not automatically give up their positions, so R1 will not become the DR or BDR. Therefore, A and B are incorrect, and F is correct. If you issue the clear IP OSPF process command on R4, the current BDR, R3, will automatically become the DR, not R1. Therefore, E is incorrect. However, if you issue that command, when R3 becomes the new DR, an election is held for the new BDR. Since R1 has the highest priority, it will become the new BDR for the segment. So D is correct. That's all for the quiz. Let's move on to a bonus question in Boson ExSim for CCNA. Okay, here's today's Boson ExSim practice question. You issue the show IP OSPF interface fast Ethernet 01 command on router 1 and receive the following output. Here is the output of the command, and here's the question. Which of the following statements is correct? Select the best answer. Okay, pause the video now. Read each of the statements and select the best answer. Okay, let's check. So I believe the correct answer is D. First, let me explain the incorrect options, and then I'll go on to D. First up, A says router 1 is the DR for the segment. Well, it says right here, router 1 state is DR other, so that's incorrect. B, router 1 is connected to a point-to-multipoint network. It says here that the network type is broadcast, so that's incorrect. C, router 1 is configured with incorrect timer settings. You can see the timers here, they are the defaults. Also, router 1 has 5 OSPF neighbors, so I don't think there is any problem with router 1's timer settings. E, the BDR has a priority higher than 50. You can see here that router 1's priority is 50, and it's a DR other. But the BDR doesn't necessarily have a priority higher than 50. It might have the same priority as router 1, 50, but a higher router ID. So E is incorrect. Now, why do I think D is correct? The key to this question is knowing the difference between an OSPF neighbor and adjacency. Sometimes those words are used to mean the same thing, but technically speaking, in OSPF they are different. Look here in the output. neighbor count is 5, adjacent neighbor count is 2. So although router 1 has 5 OSPF neighbors, only 2 of those are adjacencies, full adjacencies in the OSPF full neighbor state. This number 5 includes not only the full adjacencies with the DR and BDR, but also router 1's DR other neighbors. Remember, a DR other will only reach the two-way state with another DR other. So to summarize, router 1 is a DR other in this OSPF broadcast network, and DR others can only establish adjacencies with the DR and BDR, 2 routers. So I chose this question because I wanted to make it clear the difference between a neighbor and a full OSPF adjacency. So I'll click on Show Answer, and the answer is correct. Okay, pause the video now if you want to read Boson's explanation here. Also notice that it includes a reference to some Cisco documentation about the Show IP OSPF Interface command. And this Cisco documentation, as I have said before, is available free online, and it's another great study resource. Okay, so if you want to get a copy of Boson ExSim, please follow the link in the video description. As I've already said, these are the practice exams I used when studying for both my CCNA and CCNP, and I highly recommend them. So once again, follow that link in the video description. There are supplementary materials for this video. There is a flashcard deck to use with the software Anki. There will also be a packet tracer practice lab, so you can get some hands-on practice. That will be in the next video. Sign up for my mailing list via the link in the description, and I'll send you all of the flashcards and packet tracer lab files for the course. Before finishing today's video, I want to thank my JC and P level channel members. Recently, I've noticed an increase in the number of channel members, and I'm so thankful to all of you, both JCNA and JCNP level members. Previously, I read out the names of all the JCNP level members one by one, but the list is getting longer, so I'll just leave the list up here. Your support helps me keep making and releasing these videos every week, so I'm really grateful for your support. This is the list of JCNP level members at the time of recording, by the way, August 23rd, 2020. If you signed up recently and your name isn't on here, don't worry, you'll be in future videos. Thank you for watching. Please subscribe to the channel, like the video, leave a comment, and share the video with anyone else studying for the CCNA. If you want to leave a tip, check the links in the description. I'm also a Brave verified publisher and accept BAT or Basic Attention Token tips via the Brave browser. That's all for now.